Today's lecture is about life in extreme dimensions. Dynamical system is a state space. Some curly M for a manifold, because state space is not necessarily Cartesian R to the D space, but could be something curved. And a law of evolution. This could be Newton law, or it could be Navier-Stokes, or could be Young-Mills, or could be whatever equations describe how things change in time on this state space. Physicists often call this phase space. State space is a word that's used by engineers, people who do control theory and sophisticated engineering. Phase space in this course will be only used for Hamiltonian flows, where the word came originally. But the world of dynamical systems is much richer than just mechanics. Mechanics is very important, quantum mechanics is very important, but there is much more to a world of systems which we can evolve. And the idea of the state space, it's typically something, for example, if you look at the solar system, it's something that has some number of coordinates, x1, x2, then of course I cannot draw the rest, and xd. A point in this state space uniquely specifies the state of the system. So in case of a solar system, it would be positions of all the planets and the sun at a given instant, and their velocities, their momenta. So, usually in your introductory courses, this is 2 or 3 dimensional. Every point in a state space is unique. So if I'm trying to specify weather in Chicago, I might mean 10 billion points specifying all kinds of measurements of winds, temperatures, pressure, velocities over a large grid. If I'm just doing harmonic oscillator, maybe just 2-dimensional. And this is a map. What it does is, if this is our state space, it takes a point in state space and it maps it to some other point. And it tells us what happens in time. We assume that dynamics is deterministic, which in this case means that every state has an initial unique trajectory. If we take the set of all points from minus infinite time in our past to plus infinite time, that's an invariant set, because under time that doesn't change. And that means that the state space is really filled by spaghetti, and each of these spaghetti is unique and never intersects with any other one, because that would violate determinism. We would at the same point have 2 futures. So it's a bowl of spaghetti. And as a scientist, and especially if you're a mathematician, you're tempted to immediately go and classify all possible bowls of spaghetti. And that's a fool's errand. It is undoable. So you have to make your goals much modest, and you can say, well, I'm looking at a lizard in the sand, and I want to see how I can describe the motion of that lizard, or I'm looking at a chemical reaction, and I want to see how the chemicals change in time. You have to focus on a particular problem. Every nonlinear problem will require thought. Theory of nonlinear dynamics cannot offer you a cookbook recipe that solves all problems. All we can offer you is ways to think about your problems, but every problem will require real thought. There is no magic bullet of any kind. And today I just want to emphasize one feature of it. I would like to tell you how we have learned to think about high-dimensional spaces. And to explain why high-dimensional spaces, I'll take a very nice example, very simple example, which is called a Bunsen burner. It's a ring. You can do experiments. In some sense, you do it in your kitchen often if you have a gas burner. It's a ring. Gas comes out of it. There is oxygen. The thing burns. And if it goes out slowly, it'll burn at the same height, but as you turn on the gas, you know from experience it'll start to flutter. So that's a fluttering flame front. This has a name of few people who wrote the equations that describe it. It's called Kuramoto-Shimoshinsky. It's a thing that they use in combustion theory when they design, in rocket science, when they design engines. The way you think of it as a mathematical model of combustion is you think of the velocity of the front. So not the height at the instant, but how quickly it's changing. And there is a spatial coordinate x, and this thing changes in time. So this we'll call configuration. If you're flying a plane through the air, then this will be 3 velocity vectors of the fluid, in this case air, moving around the wing. And this will be 3 position, and there'll be only 1 time in that case as well. And if you do experiments with this, it's quite beautiful. And numerical experiments are quite easy to do. The equations are good, and I've used them in undergraduate nonlinear dynamics courses. Example of dynamics. Lots of people like this system because the equations, which I will not write at this point because they're not important, we only need to think about describing the states, not the evolution so much. The equations look very much like fluid dynamics, except in 1 dimension than 3 dimensions. So it's much easier to start with that than to work with the 3-dimensional Navier-Stokes, etc. So it's a good thing. It has applications in combustion, and it's a good model to work with. And now let's think about what is the state space. Now you might think the state space is just this x. That's the length. There's a perimeter of this burner. So maybe I should be more specific. X is defined on integral 0 to L. So that's the length of this thing. It's not essential, but it's convenient to study a Bunsen-Burner case in which you have no singled out point on perimeter, so the thing is periodic, meaning that if I look at x plus L, so I take the x, I go all around, I come back to the same point. At instant time, that's the same as you. So you would say, okay, here's how we think about it. You know, this is awkward looking from onto a 3-dimensional burner. You know, I'll just slice it, open it up, take a coordinate x here, going from 0 to L. And then the velocity of this thing will be something. And looking at the flame, I know it won't be infinite velocity. I know the flame front won't go crazy. It'll move at some range of speed, so there'll be some range of speeds. And at instant t, this is the state of the system. Now, if I blink and look at it again, a second later, it'll typically, look recognizably the same, but it'll be every place different. So this is 2 x at t1.